Hi everybody, welcome to another video in Calculus 1, section 4.2, what derivatives tell us. So this is a very long section. First we learn about what the first derivative tells us in terms of graphs, and then of course later on what the second derivative will tell us in terms of graphs. Right, the first part, the first derivative. Before we actually go there, let's define increasing and decreasing function. So suppose a function is defined on an open interval. The function is said to be increasing if f of x2 greater than f of x1 for x2 greater than x1. So, and decreasing if we have that. Of course, but in terms of graph, increasing, decreasing. It's obvious, right? Increasing going up, decreasing going down. So if we have the graph, that's easy. Now, in relation with derivative, what do we have? So notice that if anybody asks you what is the derivative, because the first thing that comes to mind is the slope of the tangent line. So if we draw this derivative, we draw a tangent line for the function like that. Or like that. Here the tangent line goes up. The slope is positive, so derivative is positive. Here the function, here the tangent line goes down. Slope is negative, so derivative is negative. So that ties exactly to increasing and decreasing. So when it is where derivative is positive, the function is increasing. Where derivative is negative, the function is decreasing. Right. So derivative is related directly to increasing and decreasing of a function. So there's no surprise there. Now find the interval of the function on which it is increasing or decreasing. Right. Once again, this type of problem is not difficult, but usually a little long. So I divide in two columns. So we asked to find the interval where the function is increasing or decreasing. So meaning where the derivative is positive, where derivative is negative. But before we can say if derivative is positive or negative, first thing we need to determine is where is that equal to 0 or where is that does not exist. So if we have a function or a derivative, therefore possibility equal to 0, does not exist, positive or negative. We have to do the first two cases first, where it's equal to 0 or does not exist, as related to the previous section, section 4.1, when we say derivative equal to 0 or derivative does not exist, and if it is in the domain, then we're talking about the critical points. So exactly that's what we do here. So we're going to find derivative does not exist, derivative equal to 0, and after that we can determine where is positive, where is negative. So again, for possibility equal to 0 does not exist, increasing, decreasing, positive, negative. Usually when it is equal to 0 or does not exist, it occurs at a point where positive or negative, usually for an interval. Right. So find the interval for which the function is increasing or decreasing. So the first thing we do, of course, is find the critical points. But we're not going to say it critical points for a reason. So first we just said the first step is find. I'm not going to say critical points, but we determine that later. But regardless, we're going to take derivative, and after that equal to 0 or does not exist. But what we find there, I'm going to put it back later, right? So derivative of that gives us 6x squared plus 6x. So that is the derivative equal to 0 does not exist. So equal to 0. So I just divide by 6 on both sides. Factor out an x. So I have x equal to -1 and x equal to 0, or x plus 1 is 0. So if x equal to 0 or x equal to -1. Right, where it does not exist. This is a polynomial. It is defined everywhere, so there will be nothing here. So it is defined everywhere, so we do not have anything here. Right. And also, after that, usually we will check to make sure that this point belongs to the domain if we find the critical points, right? But in this problem, why we don't have to check for the critical points? So let's go back to the definition. We've back to the problem first. So we asked to see where the function is increasing or decreasing. So an interval for increasing and decreasing, right? And the definition is it is only defined on an open interval. So since we are asked to find an interval, we are not asking to find the points. So we don't need to know that if the point belongs to the domain or not, right? So here's the little note here. We are asked to find an interval. So in that case, we do not need to know what happens at the point. So we don't really need to check to see if the point actually check the values of the function. So that's all we need. So for an interval, we do not need to check for this point to belong to the domain or not. To find critical point. So we do not need to find critical point. So what do we find here? Right. So what we find here, we define that to be partition numbers. And partition number is where derivative equal to 0 does not exist. Don't really need to be in the domain. So what we find here is find partition number for the first derivative. So partition number, just by the name of it, we just need to know where we divide the number line. So usually we will check to see the values of the function, but we do not need to. So in this case, for partition numbers, and I'm going to write a little note here for partition number. We only need equal to 0 or does not exist. Don't need to check for the points because we only need to find an interval, right? Don't need to check at the points. Right, so that's what we have in this problem. Right, so that's the first step, find partition numbers. And after that, we will find the interval where the function is increasing or decreasing, right? So 2 is either increasing or decreasing. So I'm going to put in a sign chart, not the table. This is a sign chart. So we draw a chart. So on this sign chart, the first row is going to be x. The second row is the derivative. In this case, we have the derivative is 6x squared plus 6x. Now, and the first line here is the number line. Now on that number line, we're going to put partition numbers. X equal to 0 and x equal to -1. Right? -1 first and then 0. We call partition number because those numbers divide the number line. So when x equal to -1, derivative equal to 0. When x equal to 0, derivative equal to 0. So we indeed it divides the number line like that. Now, so again, for possibility equal to 0 does not exist, positive and negative. So we took care of the cases where it is equal to 0, does not exist, there is none. Now we just need to test, need to check if it is positive or negative. So in that case, we will pick a numbers in between those numbers. So I'll just choose a number, and this called test point. Just pick a number between negative infinity and -1. I choose -2. Between -1 and 0, how about -0.5? Between 0 and infinity, let's choose 1. I'm going to test these values into the derivative. Again, I'm going to do the list stat, enter. Let's clear the list. Clear. Right. -2. -0.5. 1. Evaluate. When we evaluate, highlight the list and enter the function 6 and 1 instead of x. You have to use A1 though, which are those numbers. Right, so all we need is positive or negative. And according to the theorem we have here, if it's positive, it is increasing. If it's negative, it is decreasing. Positive is increasing. So in this case, we will draw the sign chart, and from here the answer is clear. The question is where it is increasing. We can answer that as an interval of x from -infinity to -1, or from 0 to infinity. Notice that I do not write the union here because it is increasing here and increasing here, not increasing all the way. And decreasing will be from -1 to infinity. -1 to 0, I mean. So, simple enough. If we only ask to find in the interval where it is increasing or decreasing, that's all we do. Don't need to check for the points, because the way we define it is on an open interval. So, if we ask for increasing and decreasing interval, that's all we do. Right, so that's the first sample. Right, we will have a few more samples of this, but then we go to something else. Local maximum and local minimum in relation to derivative. Right, there will be a lot of this. So we say there's a lot of scenarios here, but we will have the local max if we have positive to negative, meaning that if it is increasing, decreasing, there will be the max. Likewise, we have the local mean if it is decreasing and increasing. So, even though we didn't answer the question, but if the function goes like this, there will be a maximum here and then a minimum here, right? Intuitively, if we have the sign chart, we can tell where's the maximum, where's the minimum. So essentially, that is what the first derivative test is. So in order to find the local maximum or local minimum, we can use the first derivative test. This is a term. Suppose the function is continuous and containing on the interval that containing the point C, except possible at C itself. Now, if we change from positive to negative, then this is a local max. So difficult to write, to say like that, but it will be easy to say the maximum where we have increasing, then decreasing. There will be a maximum there. Likewise, if it is decreasing and then increasing, then there will be a minimum here. So that makes sense. When we draw the graph, we can see directly, see it right away. If the signs do not change, so if we go from positive to positive, like increasing and increasing, then there's no local extreme values there. So there's not maximum or not minimum if the sign do not change. Only do that when the sign changes. Right. Now, we have an example here. Consider this function. Find the interval where the function is increasing, where it's decreasing, and then identify the local extremum. Local extreme, meaning either maximum or minimum, local max or local min. Right. So, first, if we ask to find an interval, we do not need to check the point. So we don't need to check for points. However, in this second part of the problem, we ask for the local extremum, local max or local min. The nature of those are points. So we did, in this case, we do need to check. So if the question asks you to find the local maximum or local minimum, we have to check the points. So in this case, definitely we need to check the points. If we find an interval, we don't need to, but if we're trying to find local max or local min, we need to check for the points. Right. So the first step is find partition numbers if for interval. But in this case, since we need to check the points, so just find the critical points. The first step here is find critical point, because we do need to check the points. This is because if we ask to find interval, we don't need to. In that case, we just need partition numbers. Right, derivative. Right, that gives us 12 x cubed minus 12 x squared minus 12x plus 12. So we have derivative. I'll just need to make it equal to 0 or does not exist. So equal to 0 does not exist. In this case, that will be none because that polynomial defined everywhere. So 12x cubed minus 12x squared minus 12x plus 12 equal to 0. First of all of them divisible by 12, so I will divide everything by 12. X cubed minus x squared minus x plus 1 equal to 0. Now this is a cubic equation, so let's see the graph. So look like that. So if you see the x-intercept look like this, negative 1 and 1 here. So in this case, if we need to solve for that, factor by grouping the first two and the last two. The first two, they have x squared in common. So we will have x minus 1. And then this 2, I will factor out the minus. I will have x minus 1 equal to 0. Both of them have x minus 1 factored out. X minus 1. And then x squared minus 1. Don't worry, we have enough space if we continue on the next page. Right. 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 So I will let that equal to 0, that equal to 0. So I have x equal to 1, or x squared equal to 1, and if I didn't say that before, I don't think I said enough. Take square root on both sides. We have x plus or minus square root of 1 or plus or minus 1. So bottom line is we only have x equal to 1 or x equal to negative 1. But in this case, we have x equal to 1 show up in two different places. So that's why we have an even root. Therefore, it touches the x-axis and then bounce. Right. So, take derivative. That's what we have. So those are the points. Now, since this is critical point, we do need to check. for 1 and -1, and I put in the original function. Original function is that. So I will check for the original function. So when x equal to 1, put 1 in here. So I can just say 1 and -1. And I just use the list. -1 and 1. Check with original function. Original function 3 x1 to the 4th power. I use L1 instead of x, minus 4 times L1 cube minus 6 L1 square plus 12 L1 plus 1. And then I have -10 and 6. So f equal to 1 is x equal to -1 is -10, and f equal to 1 is equal to 6. Right, so we have those points. Of course, those are defined, so we have two critical points, right? So those are defined. We don't even need to write that, but that gives us critical point. -1 and 1. Right. So that's the first step. Find the critical points. The second step is put in a table. I mean the sign chart. So second step is do the sign chart. So we can find the maximum, minimum, or increasing or decreasing. And the sign chart for the derivative, of course. So let's draw the sign chart. So x, the derivative is 12x cubed minus 12x squared minus 12x plus 12. 12x cubed minus 12x squared minus 12x plus 12. So that is the derivative. And the points we have, -1 and 1. By the way, whether it is the critical points or not, we still need to put those points. Because we do need all the partition number. So whether it is defined or not, even though if it is undefined in the domain, we still need to put those on the number line. Because we need to find the interval, right? So when x equal to -1, the derivative equal to 0 and equal to 0. So we need to divide the number line like that. So we'll make a table. we need to see where is that positive and negative. So we need to do test point for the derivative. So just pick a number between negative infinity and negative 1. So I choose negative 2. Between negative 1 or 1 is 0. Between negative 1 and 1 is 0. And 1 to infinity, I will choose 2. I put those points into the derivative here. So again, start, edit. Let's clear the list. Clear and clear. Right. Now, the points negative 2, 0, and 2. Right. The derivative that we will test, highlight the list 2. We have 12 times L1 cubed minus 12 L1 square minus 12 L1 plus 12. So we have negative, positive, and positive. So, and if it's negative, it is decreasing. Positive, it is increasing, and keep increasing. So obviously, when the sign chart goes like this, here we have the local minimum, right? And there's nothing here because the sign do not change. If it just keep increasing like this, there's no maximum or minimum here. So there's only one minimum. Right. So now we write the answer. Where is that increasing? Right. Do not write negative 1 to infinity because there are two intervals. Remember, it have to be on an open interval. So from negative 1 to 1 and from 1 to infinity. That is where it is increasing. Decreasing. Decreasing is from negative infinity to negative 1. Is there a local max? There's none. How about local mean? Yes, there's one. When x equal to negative 1. Now we see when x equal to negative 1, what is the y values equal to? So that's why we check it. Not only we check to make sure that it is defined, we find the values. So potentially later on, if it is a maximum or minimum, we know exact values. We know the values. In this case, negative 10. So that's just from there. Remember, local maximum, local minimum are points, and those points belong to the original function. Right. So quickly, just graph the function and see what happened. The original function. This is the original function. 3x to the 4th minus 4x cubed minus 6x squared plus 12x plus 1. And let's see the graph. You see, when x equal to negative 1, y equal to negative 10, and when x equal to 1 is equal to 6. But 6 is not the maximum or minimum because the function keep increasing and then increasing. So that works, right? So whether we find increasing or decreasing, local max or local mean, we can use the sign charts for the first derivative. Negative is decreasing, positive is increasing. Once we have the sign chart, it's easy to determine if it is the maximum or the minimum. And usually we check to find the values because later on, if we have the maximum or minimum, we can put in to find the values. Right, so that's what we have, that one. Let's go to another example. Consider the following function. Find the interval where the function is increasing or decreasing. Locate local max and local mean. So pretty much because we need the local max and local mean, we do need to check the points. But increasing, decreasing, local max, local mean, all of them has to do with the derivative. Right, so first we do is find critical points or partition numbers of critical points. Partition numbers for the intervals and the critical points for the local max and mean. Partition numbers for increasing and or decreasing. And critical points for local max and local mean. Right. Either way, we start with the derivative equal to 0 does not exist. So that is the function. I'll find derivative. I will use the quotient rule. Even though we can just use the chain rule. Right, derivative if that's not right, and just because those almost the same. The only difference between them is the domain. So either find partition number slash critical points. Right, derivative is going to be the quotient rule because it is the quotient. U prime v minus uv prime over v squared. Right, so do this and we have 0 times anything is 0, negative 2x. The bottom, x squared plus 1 squared. Right, so that is the derivative. Now, once we have the derivative, to find partition number slash critical points, we just find it when derivative equal to 0. Or does not exist. Right. So equal to 0 is where the top equal to 0. Divide by negative 2 on both sides, we have x equal to 0. The bottom equal to 0, where does not exist, meaning bottom is 0. X squared plus 1 square equal to 0. Take the square root on both sides. I do that every time. Don't forget the plus or minus. Right. Move to negative 1. and once again plus or minus both sides on one side. So x equal to plus or minus square root of -1. So when we have the negative inside the square root, it is imaginary. So in this case, we don't count imaginary solution. So this will be not real. So we're not going to even count that. We only have x equal to 0. Right. Next, we will check with original function. Only for x equal to 0. So I put 0 in for x. And that's just 1. So yes, it is defined. So we do have a Greek component of x equal to 0. Right. And it asks you what is the partition number also x equal to 0. Right. Next, we'll go to the sign chart. For the derivative. So the derivative is this, -2x x squared plus 1 square, right? We do have the whole number line here. Partition numbers or Greek component, just 1, 0. And when x equal to 0, the derivative equal to 0. Right, now test them. Test point, -1 and 1. We'll do because we're going to test for that derivative. Between -infinity to 0, we can choose -1, and between 0 and infinity, we can choose 1. So just put the book underneath, so just like zoom in and out without actually do anything. Right, so hit start, edit, or in this case simple enough to put the -1 in here and 1 in here. If I put -1, we don't even need the calculator. No, let's do this by hand. If I put in -1, I have -2 times -1 over -1 square plus 1. At the bottom, I don't really worry about that because the square here, the bottom is always positive. So I just need to know what happened on the top. Negative times negative is positive. Positive divided by positive is positive. And if we put 1 in for x, like I said, the bottom doesn't matter. The bottom always positive. So we're going to have negative divided by positive. So it's going to be negative. If we use the calculator though. Clear enter, clear, enter. So we'll put -1 and 1. For -1, the function is -2 this one divided by this one square plus 1 square. So in this we have positive and negative. Positive is increasing, negative is decreasing. So in this case, the answer will be increasing, from -infinity to 0, decreasing from 0 to infinity. And is there a local max? That would be yes, because if it go like this and then go down, so there will be a maximum here. Local max at x equal to 0. And we did find the values when x equal to 0, the function equal to 1. So we say local max equal to 1 at x equal to 0. And local mean on the sign chart, there will be none. So no local mean. Right, so that's what we have. If we want to test, we can put in the graph and see if we do have what we similar to the sign chart. 1 over x squared plus 1. So as you see, let me zoom in. So it is increasing from -infinity to 0 and then decreasing. And that will be the maximum when x equal to 0, y equal to 1. So maximum is right there. So it is consistent to the sign chart that we have. Next, this theorem. This theorem says one local maximum implies absolute extremum. So local extremum implies absolute extremum. The key word here, of course, is 1. So suppose the function is continuous, has exactly 1 local extremum. Then if it is the local mean, it will also be the absolute mean. If it is local max, it is also absolute max. So in that case, we will find local max, we will find absolute max or absolute mean exactly the way as we find local max and local mean. Right, so let's look at the problem. Why do we need this theorem? So find absolute maximum and absolute minimum for this function on the interval. Now that is the problem. This interval from -infinity to 0, this is not a closed interval. If it is a closed interval, there will be a maximum, there will be minimum for sure, but it is not a closed interval. So there may not be a maximum or there may not be a minimum because this is not a closed interval. So that's the first observation. The second observation is that if we find absolute max and absolute mean, this is from previous section, we will find the critical point, find the critical points in the interval and then test them in the table. So if we put them in the table, we have to know the endpoints and the critical point in between. This problem, we don't have the endpoints because the interval is not closed. So there are two reasons that in this case we cannot put in the table because no endpoints to check. So in that case we have to find it differently. Right? So let's just write this little note here. So there's no endpoint to put in the table. For absolute max or min. So we have to do it differently. They still be able to do that, but we'll talk about that in a minute. So we still do this kind of like what we did here. So we have to use the theorem here. Right. So let's do that. Regardless, the first thing we do, of course, is the derivative. So first, as most of these problems are long, so let's divide into two columns. First step, of course, is find partition number or critical point. Because still take derivative at the first step. Right, u is equal to x squared plus 9. Derivative is 2x. V is x. Derivative is 1. So product rule, I mean quotient rule. U prime V minus U V prime over V square. Right. That gives us 2x squared minus x squared negative times positive is negative over x squared at the bottom. Right, combine the top. We have just x squared minus 9 over x squared. Right, so that is derivative. So as always, for this kind of problem, equal to 0 does not exist. We see this many times. Equal to 0, meaning the top equal to 0. So I have x squared equal to 9 and check the square root on both sides. Don't forget the plus or minus. So I have x equal to plus or minus square root of 9, or x equal to plus or minus 3. And then derivative does not exist, meaning the bottom equal to 0. In this case, x squared equal to 0. Once again, take the square root on both sides. So if x equal to plus or minus square root of 0, which is still 0. So we have those points. Right. And then we'll check. Because potentially it might be a maximum or a minimum, right? Check. So what do we check here? By the way, this problem we are given the interval negative infinity to 0. So obviously here we check only one of them satisfy that condition. So we check for that, and in this case only x equal to negative 3 is between negative infinity to 0. So only x equal to negative 3 is in the interval. So in that case, let's find still just find the values when x equal to negative 3. Put negative 3 into it. Original function. That gives us 18. Equal to negative 6. Keep that in the back pocket. We might need to use that. Right, next. Usually when we try to do this absolute max and absolute min, we will use the table. But in this problem, because we don't have the endpoints, so we can only do the sign chart. So if we know the endpoint for maximum and absolute max and absolute min, go to the table directly. We will review this again in section 4.4, I think. But for now, just do the sign chart for the first derivative. The difference in this problem is that for x, it goes from negative infinity to 0, not from negative infinity to infinity. And in that interval, we only have one number, critical points. And then the derivative that we will test is, this is the derivative. Notice only from negative infinity to 0. Right. Test point. How about negative 4 and negative 2? Put in there into the derivative. Negative 4 and 0 and negative 2. Right, the function or the derivative in this case, x squared minus 9 divided by x squared. I will just, to be safe, I put in the parentheses. Right, positive, negative. By the way, when x equal to negative 3, derivative equal to 0. Yeah, that's what we have here. So positive and negative. So definitely, sorry. I jump ahead of myself here. The sign chart though. Positive, negative, increasing, decreasing. If it go like that, that will be the minimum. I mean the maximum when x equal to negative 3, and then no minimum. Right? If it go like this, there can only be a maximum there, and there's no minimum because the function going down and then keep going down like that. There will be no minimum. So I will write a local max will occur when x equal to negative 3, and we checked that earlier. It is negative 6, so I have negative 6 as a local max, and when x equal to -3, and then no local mean. Then we say that's not what the question asks. The question asks us to find the absolute maximum and absolute minimum. But that's alright though, because in this problem we only have one critical point in the interval. When that happens, local max is also the absolute max, local mean is also absolute mean. Right, so here's its important part. Since there's only one critical point, and we have to have that one critical point in the interval. Since there's only one critical point in the given interval, local max is also absolute max, local mean is also absolute mean. That's why this theorem is very important. Absolute max for this problem is equal to -6 at x equal to -3, and that's all we have for this problem. Right, so typical problem, if we don't have the endpoints, then we have to do the sign chart instead of the table, because we cannot really put that on the table. If we really want to put that in the table, still fine though. We do it like this. X will approach into -infinity, x equal to -3, and x will approach into 0. 0 from the left side. And then if we find the limit for this condition, yeah, so if we find the limit, we still find the values. And if you find the limit when x go to -infinity, x squared plus 9 over x, and we split x squared over x, 9 over x. X squared over x is x, 9 over x. Now, when x go to -infinity, find 9 over infinity is 0. So this go to 0. So this will go to -infinity because x go to -infinity. 9 over infinity, that goes to 0. So I have -infinity here. Likewise, if x go to 0, then this will be 0. 9 divided by something go to 0 will be infinity. So either case, we have -infinity. If x go to 0, we do the same thing. Split them. And when we have this, put in 0, of course that gives us -infinity. And then we have -6 here. So because -infinity, there is no local minimum, but there is a local max of -6. Of course, the absolute max of -6. That's what I should say, because we're using the table. So absolute max is -6 when x equal to -3. So if we don't have the endpoints, we have to find the limits. In that case, use the sign chart. It's a lot better. Once again, if we have exactly one critical point in the interval, then the local max or local mean is also absolute max or absolute mean. So that's the first part of the section. What we get from the first derivative. Now, what do we have for the second derivative? Second derivative. Right, before we go to do anything, define concavity. So concavity. Let f be differentiable if the derivative is increasing. By the way, this is how the book defines concavity. If the derivative is increasing, then it is concave up. If it is decreasing, then it is concave down. If the function is continuous and the function changes concavity at the point either up to down or down to up, we have an inflection point there. Right. So of course, the derivative is increasing, derivative is decreasing. So in that case, that's certainly the way to define concavity. But in terms of graph, that is not very particular helpful. So in that case, an alternative definition to that is, let's say if we have the part of the graph like this, I will draw a tangent line. If the graph above the tangent line, that is concave up. If we have the function going like this, and I draw a tangent line, if it is below the tangent line, that is concave down. So this is the first note here. Concave down, tangent line is above the function. And concave up, the tangent line is below the function. So it's just like if we have the function concave up is when we bend it up, concave down is where we bend it down. Below the graph of the function, that's what I should say. But that I think is the better definition in terms of graph. Right, now in terms of derivative, in particular derivative, how is that related? Right, so we define, this is a theorem, where the second derivative is positive, it is concave up. Second derivative equal to 0 is concave down. So positive for second derivative, concave up, negative, concave down. And at the point C where the second derivative change signs, we have inflection point. Right. And unlike the first derivative, we have critical points. In this case, we don't have anything equivalent to that. But either way, since we asked to find positive and negative, remember for possibility equal to 0 does not exist, positive or negative, we have to do the other two first. Have to do equal to 0 and does not exist first before we determine if it's positive or negative. So that's exactly what we do. So let's look at one example. Identify the intervals where the function is concave up or concave down. Once again, if it is concave up or concave down, we don't need to check for the points. If we find the points, then we do need to check for the points, obviously. Right? But like I said, there is no thing equivalent to the first derivative when it's equal to 0. So in this case, we don't have the critical points for the second derivative. So we only have partition numbers. That the first step we do is find partition number. this time partition number for the second derivative. Right, so we have the function find the second derivative, because in this case we have concave up, concave down, inflection point, all of which can get from the second derivative. So the first derivative, what the first derivative gives us? Increasing, decreasing, local max, local mean, and of course partition numbers or critical points. Second derivative gives us concave up, concave down, inflection points. Right. So first we find the derivative 12x squared minus 12x, 12x cubed minus 12x squared minus 12x plus 12. That is the derivative. Second derivative 36x squared 24x minus 12. And we make this equal to 0. That's how it says. And since this is a polynomial, we're not going to have anything here because it's continuous and defined everywhere. Right, so we just need that equal to 0. I can divide both sides by 12 because we can. X squared minus 2x minus 1 equal to 0. And we should be able to factor it. Because if we cannot factor it, use quadratic formula, which I just do that now. B is negative 2 plus or minus b squared minus 4ac over 2a. That gives us 2 plus or minus 2 squared is 4, that's 12, so that's just square root of 16 over 6. So we have 2 plus or minus 4 over 6. So where we have the plus, 6 over 6 is 1, where the k is negative 2 minus 4 over 6. That gives us negative 2 over 6 or negative 1 over 3. So I have 2 points, 1 and negative 1 over 3. Yeah, so those are 2 points, and we will check with the original function. Because potentially we might have, it is inflection point, so we might need to check with the original function. So when x equal to 1, f of 1, original function is that. Another way to evaluate a function is enter the function in y equal to and then if we hit graph, of course we have the graph. But if second table, then we have the table. Or we hit second, not second, just hit trace where we enter the values for x. We have the values for y. X equal to 1 and the function equal to 6, and where the function equal to negative 1/3. I really want to get the function, the fraction here. That's alright though. We can always do this. Variables, y variables, function, y1. Let's evaluate y1 as negative 1/3. And we can convert this to fraction. Negative 94/27, which is about negative 3.48. Alright, keep that in the back pocket. So those are the points, 1 and negative 1/3. We're going to use that, put in the number line, because that's what the partition numbers for. It will divide the number line. So second, we'll do the sign chart for the second derivative. Because this problem asks us to find concave up, concave down, and inflection point. All of those come from the second derivative. If the question asks us for increasing, decreasing, local max, local mean, we do the sign chart for the first derivative, because that comes from the first derivative. Right, now to draw a sign chart for the second derivative, which is the same as for the function. Right, x negative infinity to infinity. Now we put the second derivative here. 36 x squared minus 24x minus 12. Right, there are 2 points, negative 1/3 and 0. Both of those numbers give us the second derivative equal to 0. Now the test point. The test point in between the interval, I will choose negative 1. It's not 0. The point is 1 and negative 1/3, right? So I will choose 0 in between and then 2. And then put in the second derivative. Let's go table. Of course, there are a lot of different ways to evaluate the function. Right, we're going to put in the second derivative. 36x squared, or 36L1 squared, minus 24L1 minus 12. So it is positive, negative, and positive. So positive concave up, negative concave down, positive concave up. This is the second derivative. That's what we can get from the second derivative. Not the first derivative is increasing, decreasing. So this is different thing. Now, if we go from concave up to concave down, or from concave down to concave up, both of those cases we have inflection point. inflection point, because it's changing from positive to negative or from negative to positive. And finally, we will write the answer. Concave up, negative infinity to negative 1/3, or from 1 to infinity. Concave down, negative 1/3 and 1. Inflection point, I'm going to give them as the point. When x equal to negative 1/3, y will equal to negative 94/27. And when x equal to 1, y equal to 6. Notice the context here. When we talk about concave up and concave down, those are intervals. The numbers will be between those. And when we talk about inflection point, those are points, meaning x values, y values, x values, y values. It doesn't mean x go from 1 to 6, which is not. X equal to 1, y equal to 6. Those are the points. Right. Since we enter the function, let's look at the graph. Let's zoom to the standard windows. So it looks like we have concave up from negative infinity to negative 1, and from negative 1/3, negative 1/3 to 1, it is concave down and then up. So down, up, down, and up. So concave up, concave down, and then back up. So that's what the graph look like, and we can get that from the sign chart. So bottom line, to answer the first question, the question on the title, what derivative tell us, the answer is the first derivative give us the maximum, minimum, increasing, decreasing, the local maximum, local minimum, and increasing, decreasing. That's the first derivative. The second derivative tell us concave up, concave down, or inflection points. Right. Now, this is another thing we can get from the second derivative. Is that suppose the function is continuous on an open interval that contains in C, where the derivative equal to 0. So the derivative equal to 0. If the second derivative is positive, now remember, second derivative is positive, it is concave up. If it concave up, that point is the minimum, right? Likewise, if it is concave down or second derivative is negative, there will be local maximum. If it is equal to 0, inconclusive. So the second derivative test is not as good as first derivative because there is an inconclusive case, right? And most importantly, the derivative have to exist. So in some case, the reason that we need the derivative, first derivative equal to 0, because if the first derivative does not exist, we cannot find the second derivative, right? So a drawback, two disadvantage of the second derivative test. The first one, there is the inconclusive case. The second, the first derivative has to be equal to 0. If the first derivative does not equal to 0, we have to use the table. I use the sign chart for the first derivative test. Because if we can look at increasing or decreasing like this, we can tell maximum, minimum directly. knowing if the derivative exists or not. But if we use second derivative test, we need to have the derivative equal to 0. If it is not equal to 0, then it is not a critical point. So that is not critical point. So a note here is that we have to have the derivative equal to 0. And like I said, to disadvantage of second derivative test, there is an inconclusive case and derivative has to be equal to 0. Yeah. Right. Now let's look at. So we talk about the disadvantage once again. Derivative has to be equal to 0, and there is inconclusive case. So what is the advantage? The advantage here is we don't even need to do the sign chart. Right? The nice thing about this is we just test at the point, so don't need the sign chart. So no sign chart needed. So that is the huge advantage here. But we need the derivative equal to 0, or the derivative exists. And there's an inconclusive case, of course. Now, use a second derivative test to test them. So, of course, we will find. By the way, we still need to do this first. This is the first step. So, we need to do that first. So, we take the derivative of this. I will use the chain rule. Derivative of cosine of something is negative sine of that, and then derivative of the parentheses. Put 2x here, so that gives us negative sine of 2x, and then derivative of 2x is 2. So that gives us negative 2 sine of 2x. Right. I would test at those points. As x equal to 0, the derivative at 0 equal to. So make sure it is in the radian mode. Mode radian. Okay, good. How about negative 2 sine when x equal to 0? So that is equal to 0. So yes, that check. How about when x equal to negative pi over 2? So we have that function. That equal to 0. It's good. So both of them good. So we can go to the second step for the second derivative. Right. Second derivative is the derivative of the first derivative. So once again, I'm going to use the chain rule. Derivative of -2 times sine something is -2 cosine of that times the derivative of the parentheses. I have 2x. So I have -2 cosine of 2x. Derivative of 2x is 2. 2 times 2 is -4 cosine of 2x. Right, so since both of them check from the first step, we can go to the second derivative. And that is the second derivative. Now, when x equal to 0, the second derivative is 0. So -4 times cosine of 2 times 0 and -4. So since this is -4, it concave down, and therefore we have a local max. Since it's concave down, there's a local max will occur when x equal to 0. Now we test for x equal to pi over 2. So we do that. Pi divided by 2. It is positive. Now if it's positive, it will open up or concave up, and there will be local mean will be at x equal to pi over 2. Right, now if we want to find the values, we can put it back into the original function. So cosine of 0 is equal to 1. When x equal to pi over 2, cosine of pi is -1. So in this we have the maximum minimum. So that's the nice thing about second derivative test. We don't need to do the sign chart. We only need a point. So take the derivative, make sure that they are equal to 0 before we go to the second derivative test. Second derivative test, if it's positive, concave up, local mean. If it's negative, concave down, local max. Right? Right, so that's what we have. Next, I have another example here. Use the second derivative test to test the following points. So, first derivative is that equal to 0. So that's what we need to check first. Derivative equal to. So write that in red. Right, that gives us 10 x to the 4th minus 20 x to the 3rd. Derivative of 50 is 0. Now let's test this 3 point. At x equal to 0, derivative, put 0 in here. So yes, that check. We don't need to check the derivative equal to 0. How about when x equal to 1, derivative at 1, uh, 10 minus 20, that minus 10. So that is not good. So x equal to 1 is not a critical point. So if the first derivative if the first derivative is not equal to 0, it is not a critical point. And then when x equal to 2, right, how about 2 stored to x? The derivative is 10x to the 4th minus 20 x cubed is 0. So yes, so that's good. We can continue with these 2 points. X equal to 1 is not a critical point. We're not going to test for the second derivative when x equal to 1. Only test these 2 points. So second derivative test. The second derivative, that is derivative, bring down to 4, so 40x cubed, 40x cubed minus 80x squared. Right, now I test 0 and 2. At x equal to 0, second derivative of 0, that easy. 40 0 cubed, 80 times 0 square, that is 0. Now second derivative equal to 0, it is inconclusive. And then you say, if it is inconclusive, how can we tell if it is the maximum or the minimum? Of course, we still can do that if we do the sign chart for the first derivative. But if we use the second derivative test, it is inconclusive. Right, at x equal to 2, second derivative at 2, right, just one numbers. 40 times 2 cubed minus 80 times 2 square. Except it is not 80, sorry. It's 40, that should be 16. Sorry. So that's simple math. Good thing that's still 0, which is still good, still inconclusive. But this is not 0 here. Sorry about that. That should be 60 x squared. Right, so it is 80. Now, if this one is positive, meaning it will concave up, and that means we have a minimum. So we have local minimum equal to something, but at x equal to 2. For sure we know it is x equal to 2. If we want to find the values, always have to go back to the original function, because maximum or minimum is a point and the points belong to a function. So I know that it will occur when x equal to 2. So we store 2 into x. And then original function to x to the 5th minus 5x to the 4th plus 50. This is 34. So this one we x equal to 1 is not a critical point. At x equal to 0, inconclusive. At x equal to 2 is the minimum. Right. If you want to find the minimum values, put it back into the original function. Right. So that's what we have for this one. So that is the second derivative test. Now, to summarize everything is in this chart. So essentially, this we answer the first question in the title, what derivative tell us. So I will summarize this. First derivative can give us increasing, decreasing, increasing or decreasing, a local max or min. Of course, we also have the critical point. So that's what the first derivative tells us. The second derivative give us concave up, concave down. Or inflection point. And of course, there's a first derivative test, the sign chart, and the second derivative test. Of course, those will come later when we revisit those. But the basic first derivative will tell us these things, and second derivative tell us these things. With that, I stop section 4.2 here. As always, thank you for watching, and see you in another video in Calculus 1.